Okay, this short video is over carboxylic acid nomenclature, so this adds on to all the other nomenclature rules we have at this point. Carboxylic acids have the highest priority of any functional group we've looked at, and so essentially they will always be the parent functional group. In order to name them as the parent, whatever the parent alkane was, you're going to drop the E like we always do, and for carboxylic acids you replace it with oic acid for IUPAC naming. Now, many small carboxylic acids are primarily known from their common names, and we'll go over a few common names as well. But so, for example, the simplest carboxylic acid that fire ants make use of is right here. It's a one-carbon chain, and so it would be methane. We'll drop the E and just replace it with oic space acid. And we have methanoic acid. Nobody calls methanoic acid by its IUPAC name. It's most commonly known as formic acid. And this is actually the acid that's in fire ants' saliva, that when they bite you, that's why it burns. Formic acid, the acidity of that group. The next one you already know. This is acetic acid. Well, that's its common name. Two-carbon chain. This would be ethanoic acid. Or acetic acid. And so this is the natural oxidation product of ethanol, and that's what's in vinegars, is acetic acid or ethanoic acid. And so white vinegar is purely just a dilute aqueous solution of acetic acid. A longer chain, this would be a 4-carbon chain, so it would be butanoic acid. So we can name the parents. We also should be aware of all the other substituents, and here's an example of a couple that are a little bit more complex. So try to name these. Remember, a carbonyl, this ketone is not as high of a priority as the carboxylic acid, so we name the ketone as a substituent. That would be an oxo substituent. So go ahead and try and name these, and we'll go over them. If we have a 6-carbon chain, that would be hexane, so hexanoic acid would be the parent. We've got an oxo substituent and 2 methyl substituents. Since methyl comes first alphabetically, this will be 4,4-dimethyl, 3-oxo, hexanoic acid. In the next one we have an alkene. So the alkene can be incorporated into the parent name. And so this would be pentanoic acid. Since there's an alkene, it'll be pentenoic acid. And then there's a hydroxy substituent. And so we have 2-hydroxy. The alkene would start on carbon number 4. So 4-pentene for the alkene oic acid. Now for the chiral center here, it's good practice. We have priority number 1, an oxygen. Priority number 2, a carbon bonded to an oxygen, or multiple. And then priority number 3. So we're in a clockwise manner, but the 4th priority group out at us, so we'd have to reverse our direction. 1, 2, 3 gets reversed, so we're going counterclockwise. This would be S, 2-hydroxy 4-pentenoic acid. Now when you have cyclic structures with carboxylic acids, the nomenclature is a little weird. This is not nearly as important, but I just wanted to expose it to you. And it was the same case for aldehydes, for example. Because this carbon is not part of that ring, we have to account for it in some special way. So this molecule would actually be called cyclohexane carboxylic acid. And so cyclohexane accounts for the 6 carbons here, but you can't just call it there is no such thing as cyclohexanoic acid, because that would imply only 6 carbons. And you can't have a carboxylic acid where the carbonyl is part of the ring, or it'd have 5 bonds. And so saying carboxylic acid implies that the carbonyl carbon is bonded directly to that ring. So you can have cyclopentane, carboxylic acid, etc. If there's more than one carbon in there, you would name this as a substituent. So for example, we can do a constitutional isomer. And so we could name this as 2-cyclopentyl ethanoic acid. But you won't be responsible for ones like these. You probably won't come across something like this, but you should be aware of how to name it as an acid, as this special case.